in his answers or whatever. They wanna,
Did he get it?
Hmm?
Did he
Yeah.
hear from get it?
last year, yeah.
Piece together the exact specs. You know, I'm about to go, at some point, I'll hit a famous experiment called the Rossi Hall experiment. And it's very difficult finding, these are the numbers that they used. So, we will venture forth anyway. All right, as mentioned a couple weeks ago. First off, speed of light, the letter C is used for the speed of light. And sometimes it's also used for the speed of sound as a separate, and you pick it up from context. And that's was found to be 1 over the square root of mu sub naught epsilon sub naught. And we mentioned before the fact that there's no reference frame in here, that there's nothing that would account for how fast the light is moving relative to someone else. Einstein comes along, says, doesn't matter. Speed of light is the same for anybody, regardless, whatever reference frame you're in. If you're observing it, speed of light is the same. And so he set up the following thought experiment. So this is the lab frame. I don't think we actually derived it. We got as far as, my recollection is we got as far as that time is not constant.
Yeah.
So I have a mirrored ceiling here, and I shoot a laser, and the laser is going to basically go up like this, while this is moving to the right at some speed v, and the laser will get back to the box. The distance from here to here is h. So in the lab frame, we have a box going by, it's going to shoot a laser up, the laser is going to hit the mirror and then come back to the box. There is a horizontal component to the laser light because the box is moving. In the box frame, the box is just going to shoot the laser light up and back. And that distance there is h. So the only thing that's really the same for these two situations is the distance from the box, the shortest distance from the box to the mirror. Let's take the easy one first. I know that the speed of light is going to be distance divided by time, and in this case, the distance that goes up and back, so the distance is 2h in some amount of time, and I'm just going to label this t sub p. In the frame here, well, I know, let's look at that triangle there, that the light is going to hit the mirror in half the time it takes for the box to move over here, so this is 1/2 times VAT, that is h. And so my hypotenuse here is, well, little Pythagorean theorem. So that is the square root of h squared plus 1/2 VT squared. And so in this frame over here, the speed of light is 2 times that, because it goes, that's the distance to hit the mirror and then the same distance back, 2 times the square root of h squared plus 1/2 VT squared over t. So Einstein's claiming is that the speed of light is the same in both situations. So let's set them equal to each other. No, that's not the way I wanted to do it. I want to solve for h and set them equal to each other at that point. I need to get rid of h, because that's the arbitrary piece to it. So, solving for h in this equation, I get ct divided by 2 is equal to the square root of h squared plus 1/2 vt squared. Square both sides, I get c squared t squared over 4 is equal to h squared plus v squared t squared over 4. Solving for h squared, that would be c squared t squared over 4 minus v squared t squared over 4. A chance to catch up and also tell me if I've made a mistake somewhere. From the second equation, I have h is equal to ctp over 2. So now I can just plug that into here. And so I get c squared tp squared over 4 is equal to c squared t squared over 4 minus v squared t squared over 4. And now I can get rid of my 4's. Ultimately, we're establishing that the speed of light is the same for both reference frames, so we need to basically come up with and we established last time, the time cannot be the same for both, so what is the relationship between the two? And so, let's come up with that relationship. So I have c squared, tp squared is equal to c squared minus v squared quantity times t squared. Just factor t squared out on the right-hand side. So t squared is equal to c squared over c squared minus v squared times tp squared. At this point, it's a matter of trying to get it into the form that is most familiar. We have a relationship right here, or we take the square root of both sides. So let's go ahead and take the square root of both sides. So t is equal to the square root of c squared over c squared minus v squared times tp squared, or times tp. I'm going to take what I have, this fraction right here, and I'm going to multiply the top and bottom by 1 over c squared, or divide top and bottom by 1 over c squared. And this is purely for the more common form. So on the numerator, I get basically square root of 1 over, and on the bottom, when I distribute, I get 1 minus v squared over c squared. And oftentimes it's just written as tp over the square root of 1 minus v squared over c squared. These two are the most common forms of it. Now some of these things show up again and again, so they've come up with shorthands. For instance, this relationship of speed to the speed of light. Again, this is the speed of the object, the box, divided by the speed of light. That happens often enough that they use beta for that, so that's just v over c. And so there are a number of problems where you'd be given and you'd just be told the speed is 0.9 c, or beta is equal to 0.9, as opposed to actually giving you a full number that in meters per second it's given to you relative to the speed of light. This is 1 over the square root of 1 minus v squared over c squared, or I guess we can write that as 1 over the square root of 1 minus beta squared times dv. This shows up enough that this is known as the Lyritz factor. And the symbol for it is a lowercase gamma. So that's equal to 1 over the square root of 1 minus beta squared. This equation here, the fact that t is equal to this, or that form, whichever one you like, is the equation for time dilation. So let's do a little blank jump here. So if beta is 0.1, then gamma is 1 over the square root of 1 minus 0.1 squared, which equals, so I'm going to be kind enough,
.005.
which says that the difference in the time, the ratio of the time in the lab frame to time in the box frame is 1.005. So 0.5% longer in the lab frame than the box frame, as in the times are physically different. Let's up our beta. Beta is equal to 0.5. This is gamma.
.1547.
Let's up it one more time and then I'll talk more specifics here. Beta is 0.9.
2.294.
All right. So if this experiment takes place, I'm standing in the lab and watching this box zip by, and I time it, and it turns out to be takes place over the course of 2.294 seconds. Anything that was in that box, only 1 second has elapsed. Even though for me, it's been more than 2.25 seconds. Let's say I'm here on Earth and I travel to some other place and back, and I'm gone, and I'm traveling at 0.9 times the speed of light. From my point of view, I'm gone 1 year. On Earth, 2.294 years have passed. If I have a twin, my twin is now older than I am. Actually, if this had been my brother who had done this, and my older brother who had done this, then I would now be older than he is, biologically.
Without the bragging rights.
I debate whether I could still call him, I probably would call him my younger brother, just because how often do you get a chance to do that?
Never.
That's true. We do not possess the technology to get a human up to this kind of speed. We can get other things up to these speeds, but not humans. Or any animal, actually. All right, so all of this is well and good. it's a nice intellectual exercise. Is there any experimental evidence for this? And obviously there is at some point. Einstein comes out with this in 1905.
Everyone has to think he's crazy.
He comes out with 4 papers that year, 3 of them absolutely brilliant. The 4th one I can never remember. I guess we consider him brilliant now.
Yeah.
One of them was his theory of general relativity. Let me branch into general relativity quickly, and then we'll never talk of it again, probably. General relativity works under the basis of, if I am in a building, we did not do general relativity briefly before, right?
I don't think so.
Might have gotten it in 251, but if you're in a room, you can't see outside at all. You step on a scale, and it'll, if this room is on Earth, it would read my weight of around 200 pounds. He then says, all right, suppose instead of this being on Earth, with a gravitational pull on you, this box here is accelerating with an acceleration of, well, compared to Earth, 9.8 meters per second squared-ish. And you're standing on the scale, it would read the exact same thing. Matter of fact, there's absolutely no test in this experiment. There's nothing that you can do from inside there to know the difference between these two. Putting a hole in the wall does not count. And he said, if there's no test that can differentiate between the two, then there is no difference. So, if that's the case, imagine in this situation right here, I'm shooting a laser across. Now, if this were in equilibrium, that laser would just shoot straight across. If this is accelerating, then it's not going to shoot straight across, it's going to curve. Well, if in this situation it would curve, then in that situation it should also curve. And so this gets to the idea that what gravitational force really is a warping of space itself. That light thinks it's traveling in a straight line, but it's actually curved relative to some other point of view. And that's the essence of general relativity. 10 years later, he comes up with the math, or he finds the math which had been done by Riemann. And that's general relativity. All right. The first evidence of general relativity, one of the predictions of it is the warping of space, and so light will bend as it goes around heavy, massive objects. And so you get the gravitational lensing. There's a distant star. There's our sun, our moon during an eclipse, and Earth. And so basically, you block out, I don't know, did any of you see the eclipse 8 years ago or so? Some of you did?
Years? Has it been that long?
I'm trying to remember what it was.
That was in Charleston. I think it was 2017.
2017? Okay.
Yeah.
All right.
Mm.
It's the first time I'd ever seen a full eclipse. That was absolutely spectacular.
Yeah.
So anyway, during the full eclipse, you finally get rid of some of that extra, well, basically getting blinded by the sunlight. And so you could see that this star, as it approached our sun, would curve, and then would come from the other side, it would curve, and it would look like it's in at least 2 different spots. And there are actually pictures out there taken from, I believe it's Hubble telescope, where you see this blur as it's 3-dimensional. So it's lined up just right for that absolutely incredible picture. They have no idea what's in the middle causing it. This is where in my mind, the best evidence for dark matter. So 1905 comes out with the 4 papers, including special and the idea of general relativity. 1915, he comes out with the math for general relativity. 1919 or 18 or 19, they finally see this during the eclipse. Eddington. But special relativity, that's just crazy. 1940 is the first time they actually get evidence for that. And this is the Rossi Hall experiment. We are not, Rossi and Hall are two different people. We're not in the war yet, so I'm not quite sure what physics was accomplished during the war. It was primarily
Nuclear bomb.
weapons-based. What they did is they went to Mount Washington in New Hampshire, and they set up an observatory at the top and at the bottom, and they counted these things called muons. Now, the symbol for a muon, just like a proton is a P plus and an electron is E minus, a muon, mu plus or mu minus. They're just tiny particles. And these tiny particles will decay, they're not stable. And so they will move along, and then at some point they'll just break up into various smaller pieces. And so what they did is they go to the top of the mountain here. It's around a 2,000 meter difference. They go near the top and they count muons, and I think it was like 516 muons at the top. And then they go to the bottom and they count how many are down here. Now they don't have to be the same muons. They just, if you do enough sampling up here and you say, oh, well, it's 516 muons per hour, and it's consistent, then you come down here and you measure and you get a consistent value down here. And so now, what is the prediction of how many muons should make it down here? Well, the half-life of a muon is 1.56 microseconds. That's how long they'll survive. So if I could take a muon and I could get it into a box, half of them would be gone, or there's 50% chance it would disintegrate within little over 1.5 microseconds. Well, these things, as they're traveling, are traveling around 0.99.
How do you count that many in that little time?
How do you count?
Yeah, how do you count that many of them in that little time?
You get some poor grad student to,
Well, it was like 516 per, like you said, per hour.
per hour.
Yeah.
It's possible that they counted for 15 minutes and then multiplied by 4. Okay. The way you basically count them at that point is you get a bubble chamber. You've got a superheated liquid here. And a superheated liquid is one that is above the boiling point, but you have enough pressure on it so that it's not actually going to boil. But just the slightest disturbance will cause it